Okay. Good afternoon, everyone. I think we should start this session. Uh, in this session, I will be basically talking about the activities at NITJ. But before that, it will be like a review session for all of you. And many of the things you'll find here in this presentation have been already covered by Professor. Uh, but I think I should be touching upon something, the some terminologies which have not been discussed earlier. So this is the outline of my presentation. So I will be discussing some terminologies here like 4IR and how additive manufacturing fits in there. Then I will be also talking about various steps of additive manufacturing, the technologies available. So when I talk about the technologies available, I'll be sticking to only the technologies which we have here. Most of the things that we have here are related to polymer processing. And then I will be also talking about some research issues and the activities that we do here at NITJ. Currently, more than 200 universities worldwide are actively engaged in research in the domain of additive manufacturing. So I'm particularly inspired by two universities. One is RMIT. You know the reason, and professor is here from this center of additive manufacturing, RMIT University. There is another university in USA, University of Illinois. I'm quite inspired by the kind of activities they do in the domain of additive manufacturing. Okay, to begin with, 4IR, Fourth Industrial Revolution. Uh, so this figure explains quite nicely. Here it is written it's Industry 1, Industry 2, and Industry 4.0. If we see the if we see the Industry 1.0, so here the main source of power is steam, and Industry 2.0 is electrical controls, and Industry 3.0 here main focus is on CNC, computer numerical control, PLC, things like that. And when we come to Industry 4.0, it is basically we are talking about connectivity among the devices and the equipments. So connectivity is uh, main key aspect in Industry 4.0. We down here we have a timeline, so we can see in this timeline that from 2016 onwards we are in the domain of Industry 4.0. Here I say that Industry 4.0 is nothing but it is simply the extension of the activities that we do in Industry 3.0. So all the devices and equipments are we are taking it for further. In addition to that, there is connectivity between the devices and the equipments, and some of this connectivity is wireless or wired also, and the data which is generated it is available on the cloud. Now, when we say Industry 4.0, this is a term which was coined by it was a German government initiative, Industry 4.0. Same thing when it is used in China, it's called Made in China 2025, and in USA they say it is Smart Factory. Basically, Here, in all these three different terms, the core essence is same. We are talking about connectivity between customers, products, industry, logistics. So everything is connected with each other. And now, if we look at what is happening in the industry 4.0, in the industry for manufacturing, here you will see the additive manufacturing is playing a key role in industry. The products are being manufactured by 3D printers. So this in 4IR, basically fourth industrial revolution, this is a generic term, irrespective of, so it's a generic one. So if we talk about industry 4.0, this is a German initiative, but when we talk about 4IR, this is a generic term. So it's more appropriate to use a generic term, which is 4IR. Now, here, when we are talking about connectivity, the how do we connect various devices and various machines, equipments with each other? So RFID technology plays a major role here. RFID, radio frequency identification tags. In 2014, I had an opportunity to work at NTNU, and Professor Kisheng Wang was that time, long back. He developed a smart shelf. What he was doing, on various products, he was placing RFID tag, and the moment this part was kept in the shelf, immediately it was reflected in the inventory. So the inventory was updated. At the same time, if any part was removed from the shelf, again it was updated in the inventory. So it was totally automated inventory management system. It was inventory management system happening without any human intervention. So whenever the orders went below a particular level, reorder was initiated automatically. This is one aspect of it. He was also like he implemented this entire setup in production environment also. RFID tag, the product having RFID tag when it is moving in the production shop floor. At different locations, he had placed the sensors which would detect this RFID tags, and at any point in time, the work in progress could be monitored. So he developed a very nice setup there, and it was termed, it was developed for improving traceability of the parts in shop floor. So I had an opportunity to see all these things there in NTNU University, developed by Professor Kisheng Wang. However, I was not directly involved in this process, but there I worked on a topic called condition monitoring of wind turbines with the same professor. But this professor, he had different projects, so I was on another project, but I saw all these activities which he was doing now there at the in 2014, and now RFID technology is into everything. Now coming to additive manufacturing. Now when we say additive manufacturing, there must be something opposite to this, which is subtractive manufacturing. In subtractive manufacturing, my core domain is subtractive manufacturing. It's machining. In France, I worked on machining on 5-axis machines, did performed a lot of experimentation using 5-axis machines. So my core domain is subtractive manufacturing, where in subtractive manufacturing, as you know, we start with the initial stock, which is obtained by casting or forging, and then we remove the material in order to obtain the final shape. So here, so material removal, we are removing the material. That's why it's called subtractive manufacturing. So manufacturing as such, we can have into two domains. One is subtractive manufacturing, and the another one opposite to this is additive manufacturing. So having worked till 14 in the domain of subtractive manufacturing, then I got keen interest in working in additive manufacturing. So I switched over. Not I switched over. I added another domain to my research domain, it was additive manufacturing. Now, at the moment, I work in both the domains, machining, subtractive manufacturing, and additive manufacturing. Now coming to the definition, we all know, and all these definitions come from this standard. So we are in additive manufacturing, we are producing part layer by layer, and the best part, the advantage we can say is there is no cutting tool which is used when we compare it with subtractive manufacturing. No tool is used, so any complex design can be made. So most importantly, for me to switch over, the motivation for me to switch over to machining, from machining to add another domain for me was that it required very low skill that you need to work in this domain is only you should be able to draw, you should be able to create part, 3D modeling, you should be able to do 3D modeling using any CAD software, and the intermediate steps, generating STL files, sliced, and then finally printing on 3D on a machine, it's done by the computer very easily. So the only skill that you need to have in order to work in the domain of additive manufacturing is you should be able to create CAD models. Now, once the part is created on additive manufacturing, this is not the final step. We have to do something more on it in order to get the useful part, and that step is called post processing. Some finishing operation is to be done on this, which is called post processing. Then only we get the final part. Now there are two terms which are frequently used but interchangeably, but there is a specific meaning to it. One is rapid prototyping, another one is rapid manufacturing. Rapid prototyping, you know very well, it is the first design which is created on which you will perform all designing, all testing and assembly issues you need to check. Then only once you are satisfied with the performance of the first part, then only it goes for manufacturing. Whereas rapid manufacturing, here the part which is created, that is a fully functional part, and that is used in the application, it is used uh, by the customer. So these are two specific different terms, but frequently people use it interchangeably. A care should be taken while using each of these terms: rapid prototyping and rapid manufacturing. Now here down there, we have a figure here, and professor also talked about how we can reduce the number of components when doing, like when using 3D printing. So this is same thing. If we see the part here, if I want to make this complex part using a conventional manufacturing method, then I will be doing it in different parts. I will create, say, 3 parts, and then there will be some kind of joining will be done using, say, welding, or some fastener will be used. Now if this part is having 3 parts, the single part is having 3 sub parts, then wherever there is a joint, this is a weak joint. However, now as such, additive manufacturing gives me complete flexibility to design anything and print anything. So instead of creating it in 3 parts, I can make it as a single piece. So this is what is referred to here as part consolidation. So we can consolidate the part, so which advantage is the number of components that are used in any product, it will come down drastically. Okay, another uh, application of additive manufacturing is here. We can see this is a big gear and the parts are worn out. Now one thing is we create another one and then you place it here, but here using additive manufacturing we can just we can add more material to the worn part, and then finally we can perform machining in order to repair this part. So this kind of activities uh, I have handled in past. We used cold spray. We used cold spray machines, high pressure cold spray machines, cold spray. This And we had in the past I have handled one project with Airbus company at Wits University in South Africa. So there we were adding the material and then finally adding the material using cold spray. In cold spray technology, the material is in powder form, and this material is taken, the powder form material is taken along with the jet of air or some gas, and then it is placed, then it is this is added onto the substrate. In this case is this profile. We can add the material, and once the material is added, then we can do machining in order to get the final profile. The best part of using this cold spray is, so we can retain the original properties of the feedstock, and it's oxide free. So, and it's oxide free deposits, and do not adversely influence underlying substrate material. So there are some advantages of using this technology also. Okay, next one is uh, here. So we have now the capabilities that we can print polymer and the metal also on the same setup. So this is also possible in this one example. We can see the quadcopter is being printed. The lower portion is polymer. On top of it, we can print the circuit, which is made of metallic material, and then again on top of it we can have another layer of a polymer. So circuit is basically embedded in the structure itself. So that sort of machines are now also available. Okay, now another term which is called digitally optimized design. Here here we see there are three parts again. First one is product design and development. Second stage is manufacturing, and this is what we get at the end. So end product. Digitally optimized designs. So first step is, if it is a non-additive manufacturing, what is happening? So we are doing design and development using traditional methods, manufacturing also by traditional methods, and what we get in the end is a traditional product. If we compare it to rapid prototyping, now rapid prototyping means the R&D part is done by rapid prototyping, but the manufacturing is still the conventional one. So there is no change as such in the shape and size of the final product. But now in digitally optimized design, R&D, the product design and development is also done using 3D printing. Manufacturing, rapid manufacturing is done using 3D printing, additive manufacturing. So whatever we think, whatever design we give, so we can print. So very creative designs we are able to print using this technology. And most of the time we want to work now in this domain, digitally optimized design phase. Okay, so another term reverse engineering. Frequently, initially it was used a lot. As all of you now know that in reverse engineering, we start from the final product. We start from the final product. What we do, we scan this product using, say, laser scanner, and then the 3D model is created. On this 3D model, we can add or delete some of the features, and then finally this product can be 3D printed from the 3D printed, and it can be launched into the market. So we are starting from the end product, creating designs, adding, deleting some of the features, and we are launching the product again in the market. So this way we are far ahead of our competitors. So for scanning, 3D scanners are available, laser scanners. One machine is frequently used in engineering industry, which is a CMM, coordinate measuring machine. This machine can also be used for digitizing the part. Digitizing means getting the part in 3D environment. So this machine can also be used for creating the CAD models. Okay. Now, some of the technologies, additive manufacturing technologies. So as per ISO and ASTM standard, there are seven categories, and what we do here is in the domain of, say, material extrusion. We have FDM machines, plenty of them. We have wet polymerization SLA machine, and from this category, material jetting, we have polyjet 3D printers or multi-jet printers. Whereas Prof. Mashia has discussed more about something in this domain, but we at NITJ, we are in this domain of where we are processing polymers. Very recently, one PhD research scholar, he has passed out from our department. So he has worked in the domain of VAM. What he did, we had one welding machine available with us, wire-fed welding machine, and that machine he applied. He used he controlled the axis and then made that machine to perform for use that machine for depositing the material. And now we have a setup which he created here, VAM setup. Okay, so here in the domain of FDM, so this is now we have many machines available with us here in FDM. The process is pretty simple. So we have a build platform, and there are two wires which are fed. One is the dark blue is the main wire, the build stock, and the another one is the light in color is support material. So both these materials come in the extruder, so heat is provided and the material is deposited on the platform layer by layer, and once one layer is done, the entire platform will move down and the process is repeated. Okay, this type now these machines are quite quite cheap, and our undergraduate students are using these machines extensively. One interesting activity, one project which was done by our undergraduate students is here. So they created an aeroplane, and on simple this FDM machine, and then they added all the motors and circuitry to it, and this plane, like they could fly this plane. This is just one example. Plenty of other examples are also here. Now coming to stereolithography here. So this machine also we have here at NITJ. In this we have the material is a liquid material, the polymer. So this falls under the category of wet polymerization, where polymerization is happening in the container. So that's why the name is wet polymerization. Since the polymer is in liquid form, it can provide, this technology can provide fine detailing, but the material is such that it is brittle, so we can't use this part. Like, it is not a fully functional part, we cannot use it in the application. But it is the parts which are printed here have very good surface finish and aesthetics. So mostly where we want to show the customer what would be the shape and size and texture of the product, there we use this technology. We can't use it like in the end user cannot use this the parts made on SLA as the final finished product. So we also have exposure of working on this machine, selective laser sintering, and this machine is available at another institute which is close to us. It is called CTR Ludhiana. So we have done a few studies on this machine also, and this falls under the category of powder bed fusion. Now in this case, we can see here the middle portion is where we build the part. Left and right side we have powders, and the roller will move from left to right and then from right to left. When roller is moving, it will take the material and it will spread one layer of that material in the build zone. Once one layer is spread there, from the top, laser will come and it will scan the area wherever it falls, it will be solidifying that portion. And then once this is done, now the roller from the right side is ready to take the material from the right chamber. It will roll and it will take the material to the, when it is moving to from right to left, it will take the material along with it, spread another layer on the build platform over already solidified one layer. So selective laser sintering. So this machine is that we used is from 3D Systems. Another machine we have here, this machine is available, material jetting. On this machine, if we want to produce parts like this, so we can print materials in single setup. We can have a shoe made from different material, the upper portion from different material, and the top portion also from a different material. The technology is very similar to the inkjet printer. Here we have the material, it's available in the tank. From there it's a resin tank. The material goes to the, it goes to the jet, and then it is sprayed wherever it is required to get the material. And left and right we have curing lights, which will be the material is sprayed here, and left and right lights are available. UV lights are radiations are available. It will be curing the material instantly, almost instantaneously. Now this is just shown as just one nozzle, but actually we have multiple nozzles in this. And the advantage of using this technology is we can print. The printing speed is high. We can print with different materials. These are advantages. But the drawback is the material. The raw material is quite expensive, and we have to count on the suppliers, on the manufacturers to get the raw material. Now, how we select additive manufacturing technology? There are so many technologies, 7 technologies, and out of 7, there are further subclasses. How do we select appropriate technology for our product? So here is a basic criteria. So first step is we have to select what is the material, what dimensional accuracy we are looking for, and then we see the properties. And finally, definitely, we are also interested in the visual appearance. So based upon this criteria, we decide, based upon these criteria, we decide which technology is appropriate for us. Now, coming to the research issues, additive manufacturing in general, and then I will be talking about what we are doing here. In general, there are 3 things involved in additive manufacturing. So I have categorized it like design domain. So we can perform research in design domain, then we can perform research in the material domain where we develop new material, methods, and finally we go for optimization and modeling. Now coming to the design domain, here you can see there are different designs. These are bio-inspired designs. Bio-inspired designs which are very difficult to manufacture using conventional methods. So there are many designs. Many designs have been used, but there are still many designs which are yet to be tried and tested. So there is a lot of scope of R&D in this domain when we talk about the design related issues. Now coming to material development, now this figure, it's quite, anyone who works in the domain of material science might have encountered this figure. It was given by Professor Ashby. Now x-axis we have density, y-axis we have strength. And here always the material development engineers, they want to work in this domain. So there is a big hole here. And what is this hole? They want to develop materials which are light in weight, but at the same time they have high strength. So this is the domain where still a lot of work can be done, not only in the domain of additive manufacturing, but in general in the domain of materials. Okay, here the third approach, like being industrial and production engineer, we work in the domain of design related issues. Our studies are restricted. We don't work in the domain of material development. This work we don't do it here. we work in the domain of design, we work in the domain of methods. In methods, what we are doing for each machine, different machines, we by changing the process parameters, what is the effect of that come? What is the effect of changing the process parameters on the product quality? This is what we try to assess. The where basically it is a parametric study, and then we also try to model it. For modeling, we are using different approaches, and we also try to optimize the process parameters in order to get the best results. Now, when we talk about optimization, we have to keep in mind there is no one best solution for all the activities. Optimization is basically a situational affair. Under certain circumstances, you have one solution. Under different circumstances, you have different set of solutions. So we have to be very careful when we are doing optimization. Based upon my functional requirements, my optimization will change. Okay, so these are the some of the studies which our master's students have performed in the past. So we have dealt with the empirical modeling, basically experimental work. This work we performed on SLS machine. Here we changed the process parameters, and we saw the effect of these the process parameters. These are the process parameters which are available on the machine, and we studied the responses. In responses, we studied the dimensional accuracy, surface finish, uh, and finally we optimized various parameters. A similar study we performed on FDM machine by changing the process parameters and how the part quality behaves. So this is what we have been doing. So for optimization, we used the conventional methods. We are also using evolutionary algorithm methods, AI techniques for optimization. Uh, this is multi-physics modeling. This is quite interesting. So one of our student, he also works in this domain. Here, so multi-physics modeling, analytical modeling. So we are interested in developing physics-based models, which are a bit difficult to obtain, but for engineers, it is quite challenging and quite interesting to develop physics-based models. Suppose this is one example here. We have a wire is being fed. Say we can take example of WAM. Here in this type of modeling, what we are doing is how much heat is given, how much heat is given to this wire, and when this wire is converted into say a droplet is formed, and now when this droplet is formed, when it is formed, and then when it is formed properly, how it moves down, and down there we have substrate, so it will fall on the substrate. So what is the interaction of this droplet with the substrate? So it get once it falls on the substrate, and in the meantime more heat is given to the stock. Next drop is formed, and now this drop when falls, already there is a bubble on the substrate. How this drop interacts with the another drop, how solidification is taking place, and because of this microstructure is changing. And not only this, heat is involved, so residual stresses and distortion will also happen. So all these things are of our interest, and this is what we are exploring here at NITJ. In addition to this, we also have exposure on using evolutionary algorithms. These days, evolutionary algorithms, AI techniques are being deployed in almost all the domains. Okay, now some of the ongoing research topics. Some of these topics are being handled by our master's student, and some are by being taken care of by PhD students. So this is a quite interesting study. We do quite a lot. Like any process we take, and then we check the process capability. For checking that process capability, we create parts which are shown down there, and we check what is the dimensional accuracy, what is the reproducibility, geometric features and defects. All these things we try to we try to assess. These things are also provided by the manufacturer, and one manufacturers, they will also provide all these things, all these details, but we check everything here in our lab again, just to see whether the results which they are giving, claiming, we are able to achieve or not. Then we are also focusing on developing low cost additive manufacturing setups, because that is the need of the hour, especially for us. And in this, we have developed one setup, VAM. After this presentation is over, the student who has developed this, he will be giving a presentation. So in total, there are three students who are working in the domain of 3D printing, and they will be first they will give a demonstration of whatever setup they are using. So then the student who has developed this machine, he will show you what is the setup, and then he will also explain finite element analysis. So he has done modeling part also, so he will be going through all the steps for finite element modeling using VAM. Okay. Then so one of our student is also working in the domain of sustainability analysis, and few of students are also working in the domain of selection of appropriate additive manufacturing technology using smart algorithms. And then now we have a lot of data available, and data is also available on the internet. So using that data, we can also now fix what should be the process parameters without doing experimentation using AI algorithms. This is quite interesting. We have developed this extruder. We have one professor in my department, Dr. Kapil Kumar Goyal. So he, along with his team, they are working in this domain of creating filaments for FDM machine. So they have developed this setup where they are producing basically the filaments for FDM. So this is just one such setup, but they have developed many things, many more things here in the lab in this domain of development of low cost 3D printers also. Okay, now the final goal for us is, now we want to move towards 3D printing of metals, and we want to have body implants like this. And the reason is quite obvious. Now when we are going for metal 3D printers, we require knowledge of 3D printing. So we already have now knowledge of 3D printing, but maybe in the domain of polymers. But I have no. So this knowledge, we have a prior knowledge of 3D printing available with us. We have expertise who can develop low cost solutions, and also we have worked with process parameter optimization and things like that. In addition to that, I also have experience in machining of different materials. When we want to go for metal 3D printing, so the first step is to print, and then for post processing we require 5-axis machines, or machining, some sort of machining is required. So we have all the skills available in the school, in the department, to jump into this domain of metal 3D printing, and we are quite enthusiastic. And here I would like to have the inputs from Prof. Marcia for helping us in selecting the proper machine for this work. So we have at the moment we have selected selective laser sintering, but all these metal 3D printers are quite expensive. We really want to have your inputs in this domain, sir, so that we are able to establish a full-fledged lab which will cater to the needs of our society. So this is the goal, and I think in next 1 year time we will be able to obtain. We will be able to achieve our goal. Uh, Coming to CNC machines, we have already many CNC machines available with us. Uh, the this CAD softwares, FEA softwares, we are in the process of obtaining it. But this machine we have selected, but still we have not finalized it. So here we require your help to finalize this thing, sir. Okay. Now, some of the important additive manufacturing manufacturers, I've placed it here just in case you want to see who are the manufacturers. So this is a list. We have 3D printers from SLS 3D Systems, and we have printers from Z Corporation. Now coming to the modeling softwares, because that is the only skill one should possess. So this chart is from Materialize company. So they have a list of softwares that can be used for additive manufacturing. Here at NITJ we are using Fusion 360. Online resources. So this slide is quite interesting. Here, if someone wants to work in the domain of additive manufacturing, someone is new to this domain, and so this is the best slide for him or her. You can get the software downloaded, Fusion 360, from this link. You can design the part, and then you don't have printer available with you. What you can do, you can send this part, the mod the design, to this company, 3D Hubs. So they have a database of printers installed worldwide. So you can send it to them for printing. Maybe they will send this part back to very close to your location for printing, and you get the part in almost in 24 hours. So very quickly you're able to get the part printed. And if there is someone who does not want to even design, then there is a solution here down there. You can visit this website, Things I Worse. On this website there are plenty of designs available. You can select any design, you can make slight changes and that design, and still you can get it printed. So 3D printing has a huge scope. So some of the enthusiasts say that in the times to come, companies will not be selling any products. They will simply sell the designs, and we will be printing it at our home. Like we have laptops now. Every house is having 2 3 laptops. In times to come, maybe 5 years to come, every house will have one polymer printer, one metal 3D printer, one ceramic printer. So you will simply buy the designs from the company and get it printed at home under your supervision. This is what the enthusiasts say in the domain. I don't know this will become reality, but definitely 3D printing is having a huge scope. Another scope which I see, using 3D printing, additive manufacturing, anyone can be a manufacturer, because you need just a small space, and the machines, especially the polymer machines, are quite cheap, and you can become an entrepreneur. You can become a manufacturer by just minimum investment. So this is another good part of additive manufacturing. So these are the some of the publications from our department, and that's it from my side.